everyone, welcome to Vedantu J English. I'm Diksha Kaushal, your chemistry master teacher. So everybody, today is the lecture number 2 of periodic classification, and in this lecture we are going to discuss about first thing screening effect, that is shielding effect. Then we are going to discuss about Slatter's rule, okay, and we are also going to calculate the value of sigma, Z effective, the value not only in the theoretical terms, we are going to calculate the value by Slatter's constant. After that, because all the effects are related to the screening effect, like screening effect is the base that will guide you towards all the effects like ionization enthalpy, which is very important, radius, electron gain enthalpy, electron affinity, and electron negativity, right? So everybody, do let me know in the chat box if you all are ready for the class, and is there any doubt in the last session, and can I just see how many of you have actually done the homework? Let's see that, okay? Let's see that. So yesterday's homework, so yesterday only I saw okay, Ramya, thank you so much. I saw your comment. That means the world to me. Thank you so much. That's such a beautiful comment that you have written here. Thank you so much. And none of you have done the homework. That's really, really sad. That's really sad. What can I say about it? I don't know why you don't do your homework, right? Why doing homework is such a big deal. You know, if you, wait a minute, yes, if you actually want to practice, right, I am again telling you, I have already prepared the DPPs for you guys, right? All I am waiting for you is you guys do your homework, right? So if you're not doing the homework, I am not going to provide you the DPPs, right? The DPPs are ready, all the chapters that we have done, and for the future chapters also the DPPs are already ready, right? So if you want those DPPs for totally free of cost, then you have to prove yourself. If you're not proving yourself, I am also not going to provide you the DPPs. As simple as that. The efforts should be from both sides, right? Not only from my side, right? So you still have time. I'm still waiting for that time when you will get serious, because guys, not so much time you have for your exam, right? So the answer for homework, the last homework that I gave you, this is the answer. The solution also I have written here. This is the question and this is the answer that I have given you here, right? Now, next thing is, today, whatever we discussed in the last lecture, that was about the periodic table, right? We discussed about the history of periodic table. Then we discussed the very simple thing, that is modern periodic table, the structure S, P, D, F, all these blocks, right? Yesterday's lecture was more about cramming, little bit understanding also was there to understand the modern periodic table and the stories behind history of periodic table. But learning that periodic table was more about learning the mnemonics and all that, right? But today's lecture is entirely to understand. The concepts are there in today's lecture. And a very important concept that I have told you in the starting, that is screening effect that we are going to start with, right? So if you talk about JEE, in JEE, you should know how to calculate Slatter's constant, you should know how to calculate Z effective, right? That is important for you, right? So if you talk about in board examinations or maybe at NEET level also, not that much they ask you about screening effect. But if you talk about JEE advanced level also, you should know that how to calculate the value of sigma. What is this sigma? What is Slatter constant? What is this rule, right? So firstly, we'll start with the theoretical part, that what is screening effect. Then we'll discuss the numerical part of it, right? How to calculate, the calculations part of it, right? Okay. So everybody, let's start. So the first thing is, if I talk about screening, screening is, can you see this over here, right? So we know that, for example, we are sitting like this, right? So what will happen, or let's take another example. For example, you are sitting like this, right? Or you can take an example here that you are in your class and you are in the on the first desk, and someone out there is on the last desk. right? And this is the nucleus, the teacher is the nucleus, right? So, for example, they have gone to cricket stadium to watch cricket. So, what will happen? These people who are in the front row, they will find it more easy to watch all the cricketers from a very less distance. And the people who are out there here, right, they will find it very difficult, right? That's why the seats in the front row are expensive than the seats in the last row, right? So, that means what is happening with this last row people, right? Why the prices are low for this last row? Reason being because there are so many people in front of them that are screening the who is your favorite cricketer? MS Dhoni? Let's talk about MS Dhoni, right? MS Dhoni or Shubham Gill or Virat Kohli. Let's talk about Virat Kohli, right? I have no idea about cricket, guys, right? So let's talk about Virat Kohli, right? Very famous cricketer, right? So here you have Virat Kohli, right? And now Anushka is somewhere sitting here. No, ma'am, Anushka, why Anushka will be sitting there? Anushka will be sitting here, right? So Anushka will be sitting in the front row. So Anushka is able to see Virat Kohli like properly, clearly, right? Because she is in the front row. But all the other people out there are not able to see Virat Kohli. Why a very blurry image of Virat Kohli is there? Because there is screening of so many people, so many persons that are in front of the person that is in the last row. Similarly, you have electrons, right? Similarly, there is shielding in the electrons, okay? So let's talk about that, right? So wait a minute to show you that. I'll just imagine this is firstly just focus on, just have patience, okay? You should have patience when you want to understand these kind of concepts, right? Because these concepts will be repeated again and again throughout the block chemistry, right? Whether it's P block, it's DNF block, this concept will be repeated again and again, right? So this is the nucleus, okay? So let's take an example of carbon. Let's take an example of carbon, okay? So carbon is nothing but what is carbon? Carbon is having 6 protons and it is having 6 electrons, right? I am not talking about neutrons here because the neutron is 0 charge, so that is not going to affect that much. So here you have 6 protons, right? And here what you have is, this is the n is equals to 1, right? This is n is equals to 2. This is, let's say, n is equals to 3, right? Or this you can say is other one, right? So this is how the approximate diagram that we draw it like this, right? Now, if you see, let's say, how is the electronic configuration of this carbon? Carbon is 1s2, 2s2, 2p, 2, right? This is the electronic configuration. Let's assume this is 1s, okay, this is 1s. Let's say this is n is equals to 1, this is n is equals to 2. N is equals to 3 does not have any electrons, so I am not going to draw it. And I am not drawing 2s and 2p individually here because we have seen that in quantum theory that how it actually looks like, okay? This is just a vague, blurry diagram of that thing, right? So if you see this here, in n is equals to 1, you have 2 electrons. In n is equals to 2, you have 4 electrons, right? So here I will draw 2 electrons, okay? And here I'll have 1, 2, 3, and 4. I'll have 4 electrons, right? So if you see this here, I want to see that who is shielding whom, okay? So what I'll do here, wait a minute, let us just erase this thing here. Yes, this is not even needed, so why to have it, okay? So if you see, if I want to see the screening means this is the first row person, this is the last row person. There will be so many people that will be over here, right? And let's say this is the Virat Kohli that you want to see, right? This is the Virat Kohli. Virat Kohli has a different style here, right? This is Virat Kohli that you want to see, right? So Virat Kohli is with his bat, right? He is doing like, so sixer, right? He is making sixers and all. So now what will happen? You won't be able to see Virat Kohli. Why? Because there is so much audience here. And this audience that is before you is creating a screening effect, is making this Virat Kohli very difficult for you to see, right? Now, let's see someone is out there here also. Will this, let's say this is A person, this is B person. Now tell me one thing, will this B person will have any effect on A? Will B person screen Virat Kohli or not? Will Virat Kohli, so you hate Virat Kohli, then I can take MS Dhoni then, right? Whomsoever. Okay, let's talk about Samantha. Okay, that's your favorite actress. Okay, whosoever you like the most, that's Samantha, right? So I really like her, right? So that's Samantha over here, right? That's you, and that's someone in the behind you, right? So you're almost on the last row, and there are so many people in front of you that are screening Samantha, right? But tell me, will this screen? No, because this person is behind you. How does it matter? Behind me, there are 1,000 people, 500 people, doesn't matter. Who is in front of me? That matters the most, right? That was the first thing. Now tell me one thing. In that particular row, there are, let's say this is you, this is another person, and this is another person, right? Now you are not able to see Samantha, right? Very difficult for you because of this screening. Tell me, will this person and this person have any effect in screening Samantha, right? Will this person and this person will have any effect? Someone is there on the same row, right? Behind me will definitely have no effect. But the main question is, if someone is just in the same row, right, will they have any effect? This is a complicated question. Some of you may say yes, some of you may say no, right? So the answer is yes. Yes. They will definitely have effect on you. They will definitely have effect. And what kind of effect? Not screening effect, because screening is done by these people who are in front of you, right? Who are before you. But the one who are on the same position, on the same row, how they will affect? They will repel. That means they'll be like, I want to see Samantha, I want to see Samantha. You side, I want to see Samantha. That's how they will repel, right? So these people are going to repel the other person in the same row, right? So they are also going to affect in seeing, when you want to see Samantha, you want to just have a look of Samantha, right? But what will happen here? They will cause repulsion. They will cause repulsion. Got it? So two things you have here. First is, there are people that are in front of you, and that's the hero that you are looking for, right? That's the hero. So the people who are in front of you, they will cause shielding, right? And the people who are in the same row, they will cause repulsion. Behind you doesn't matter, right? Tell me guys if that concept is clear, because same concept we are going to apply in understanding shielding effect in an atom. Okay. Yes, everybody. Abhijit, I didn't get your question. Right? Okay, Azad, then I can't do anything about it. Right? So tell me, is that clear everybody or not? Is that clear or not? Right? Now, guys, do respond, sir. NEET aspirants were not responding, and we are not even taking classes there. Right? They were not giving any response. Okay? So if you stop giving response, then we'll have to shut down the classes here as well. Right? because as teachers we can't, afford to waste our energy when the students are not interested in answering, right? So don't do that mistake what they did, right? Okay, yes. Now let's see this thing here, right? Let's see this thing here. Now I'm going to make this a little bigger, right? Okay, this, let's say, is n is equals to 1 and this is n is equals to 2. Okay, so I told you that here you have 2 electrons in n is equals to 1. This is the first electron you can write here. This is the second electron in n is equals to 1. Here you have 1, 2, 3 and 4. 4 electrons you have here, right? Now, this is n is equals to 1. This is n is equals to 2. Now, I'll ask you one by one. If I ask you that what is the effect, how many people are screening this particular electron, and I am naming it as 1. Electron 1 is screened by none because there is no electron that is before this electron. But let's say this is electron number 2, this is electron number 3, this is electron 4, this is 5 and this is 6. So electron number 1 is not screened by anyone. But electron number 1 is definitely repelled by something. Electron number 1 is not screened by anything. There is no screening. There is no electron before it. So there is no screening, but electron 2 is repelling, is causing repulsion. Electron number 2 here will cause the repulsion because they are in the same principal quantum number, right? They're in the same shell, so they are going to repel each other, right? So that is the reason if I say you have 6 protons, right? So the nuclear charge, what is nuclear charge? Nuclear charge is the attraction that this nucleus is causing on this electron. So positive and negative will definitely attract each other, right? So this nucleus is also going to attract this electron, this electron, this electron, this electron, this electron, this electron. It will attract all the electrons, right? Now, when you have this electron, we assume that because here you have 6 protons, so the attraction that we assume should be 6, right? But because of this electron 1 and electron 2 repulsion, because of electron 1 and electron 2 repulsion, effective nuclear charge is because of the repulsions or the screening. When the nucleus is not able to attract the electron with that much efficiency, right? That is called effective nuclear charge, right? If there were no electron here, there was only 1 electron in this atom, then there would be this proton will attract the nucleus with same efficiency. It's like this is your parents and this is you, right? So if let's say there is no friend, there is no one out there who is like, asking you to go here and there, do party and all of that, then there is no one, right? So you and your parents, that's it. Your parents will have full like attraction, right? They'll be able to, yes, come back home today, this Sunday, you have to come back home, right? You will go, right? But what if you have someone in your life, right, who is repelling you, is like, don't go home, right? So this is repelling. So that is why this proton will not be able to attract this electron with that much efficiency. That is called effective nuclear charge. Okay, because of the repulsion of E1 and E2, right, Z effective is going to be less than Z. Z is the nuclear charge. Nuclear charge is simple, that is what we expect. But in reality, you have Z effective. That is because of repulsions and because of screening effect, it decreases. Okay, because of repulsion and because of screening effect, it decreases. Now, if I talk about electron 2, if I talk about electron 2, it will have the same thing. Electron 2 will face repulsions by E1, right? This second electron will face repulsions by E1. There is no screening effect. So that is why Z effective is less than Z. Now, if I talk about E3, if I talk about E3, right? If I talk about this particular electron here, that is E3 over here, this particular electron, that is E3. Now, in case of E3, what you will have? Lines, I doubt I should prepare for equilibrium. Are you talking about JEE equilibrium affect my JEE preparation? Yes. Okay. So now, if you talk about I3, if you talk about I3 here, this is the thing. Now, in I3, I3, I am saying in E3, right, what you have is this E1 and E2 is causing the screening effect because they are before this. So, E1 and E2 are causing screening effect. They are causing screening effect. They are decreasing the nuclear charge because of screening effect. And E5, E6, E4, the ones who are in the same shell, they will E5, E4 and E6, or you can just write E4, E5 and E6 will cause repulsion, will cause repulsion. And because of these repulsions, because of these repulsions, and because of these repulsions, then screening effect, the Z effective is going to be lower than Z. Right? So because of screening and repulsion, Z effective is going to be lower than, Z effective is going to be lower than, yes everybody, it's going to be lower than. Is that clear to everybody? How it is going to be? Same is going to happen when you talk about E6. For E6, E1 and E2 is the E1 and E2 is the screening effect, and E3, E4 and E5 are showing repulsions here. That's how they are screening it. For E5, E1 and E2 are the screening, E6, E3 and E4 are causing the repulsions. For E4, E1 and E2 are the screening, E5, E6 and E3 are the repulsions, right? And because of this screening and repulsion, Z effective will be lower than what you think, right? Okay, time fair, don't worry, you're on time. Now, other students here, tell me if that is clear, okay? Yes, Abhijit, I definitely remember you, right? Okay, so now if you see this here, this is a very interesting meme on this. So how does shielding effect work, right? So this is the nuclear charge, right? That is attracting. This is the valence shell electron and this is the inner shell electron, right? So valence shell electrons wants to be attracted by the nucleus, but in between you have this inner shell here, right? In between you have this inner shell here, which is not, that's why, because see what is happening here, this inner shell is like the protection that you have, it's like your bodyguard, right? So this is the nuclear charge, right? Nuclear charge that is trying to affect you. This is you, right? This is you. So this nuclear charge is trying to affect you. But now what will happen, because of this inner shell electron, it will cause a shielding, it will protect the outermost electron, right? And that's how you will have a Z effective, right? Okay, everybody, right? And there is another thing how you can, understand this. So this is the milk, right, that this cat wants to drink, right? So what will happen? The cat that is near the milk, okay, that will try to drink the milk, right? and the cat that is away from the milk, definitely the milk will be left for the cat that is away, right? Similarly, for example, these are the protons, right? Similarly, these are the protons, right? So this inner shell electrons will have all the positive attraction from these protons, and very less proton charge will be available for this valence shell electrons. That's how it is called zinc shielding. Okay? Yes, everybody? Clear? Right? Yes. Uh, utilize your Sunday full day, and you have all your lectures here. Watch the lectures, and that's how you can complete, right? Okay. Now, next thing, guys, this is another way of understanding this. This is Z effect. This is your nuclear charge, and this is now let's understand what is N, what is N minus 1, what is N minus 2. Okay. For that, firstly, you have to understand the grouping. Okay. So, instead of this, I would rather teach you firstly this thing. Okay. Because grouping we will learn, because we are moving towards the numerical portion of screening effect, right? So, if you see, due to screening effect, what happens here, right? Valence shell effect electrons experiences less force of attraction which is exerted by nucleus. That means this less force of attraction is nothing, that is called Z effective, that is called effective nuclear charge. Like in carbon, you had 6 protons. You were expecting that all these 6 protons will have a force of attraction on even the outermost electrons. But in reality, what happens? In reality, you have screening effect, you have repulsions, and that is the reason the effective nuclear charge is there, because now 6 protons, out of these 6 protons, there will be something that you will subtract, and that is nothing but this is your shielding, this is showing repulsion. This sigma is showing you shielding and repulsion. Okay, so there is a reduction of nuclear charge due to screening effect, right? Reduced nuclear charge is called as effective nuclear charge. And if you see the formula here, what is Z? Z is the number of protons. Number of protons. This is what you expect, that carbon has 6 protons. It should give 6 nuclear charge to all the electrons. But in reality, what will happen? You will have Z effective, which will be decreased by an amount, that is sigma. And this sigma is called as screening constant. And this sigma is because of screening and repulsion. You can just write it here. It is because of, we also take repulsion, also we take in screening only, right? Screening and repulsion. Screening and repulsion. Okay, so that is how you have Z effective, right? Okay, everybody. That is how you have Z effective. Now, the next question can be, what is this Slater rule? This is the Slater rule. Now, let's understand how to do that, right? A rule used to understand Z effective experienced by a particular electron in an atom. We can find the screening constant using Slater's rule. Because see, if I give you any atom, let's, for example, if I give you sodium, you know that sodium has 11 electrons, it has 11 protons, right? So Z effective will be 11 minus sigma. But what is the value of this sigma? What is this screening constant? Now this screening constant will be calculated by Slater's rule. It will be calculated by Slater's rule. Okay, Slater's rule. And this is not that complicated rule. It's simple only. Just I'll make it very simple for you, right? You just have to, like, there is no room here for distractions, right? You have to be very, very fully concentrated when you are watching this particular section of this part, right? Let's understand that. So, firstly, you should know how to group these electrons, right? So, firstly, I'll just teach you how to group it, right? So, only firstly, we should learn how to group it. Grouping, first thing is to answer to grouping of, to answer this lattice constant, firstly, you should know grouping of electronic configuration. Electronic configuration, okay, electronic configuration. So I'll write it how to group it, okay. So how you will group it? First you will group S and P, then you will group D and F. That's how you're going to do it. Now I'll take one example. For example, you have, let's say, magnesium, okay. Let's say you have magnesium. So you have 1s2, write the electronic configuration firstly simply, okay. 1s2, 2s2, 2p6, 3s2. That is the electronic configuration of magnesium. Now you are going to do the grouping here. So how you are going to do the grouping, everybody? How you are going to do the grouping? This is 1s, 2s, 2p and this is 3s. So firstly you are going to write 1s. Then you don't have any 1p, so write it as it is. Now second group will be 2s2 and 2p6, right? Third group will be 3s2. That is the grouping. Now let's take more examples here for grouping. If you ask me more groupings here, let's take more example. Let's say I want to group oxygen, okay? Oxygen is still simpler. So I would ask you to group scandium. Okay, let's see, you have to group scandium. Now scandium is atomic number 21, right? Let's understand how to group it, right? So firstly write the usual electronic configuration, that is 1s2, 2s2, 2p, and here you have to write full-fledged electronic configuration, right? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1, right? Now you have to write it in this sequence. Let's see how. Firstly write 1s2, first group, then you have 2s2 and 2p6. Then third group will be 3s and 3p, 3s2, 3p6. Now as I told you, first you will see S and P, then if in that shell, this is for a particular shell, you have to write it this way. See, for first shell, you have only 1s2, so write it as it is. So second shell, you only have 2s and 2p. For third shell, you have 3s and 3p and 3d as well. So 3s, 3p, 3d, how do you write? 3s2, 3p6, write 3d1 and then write 4s2. That is how you are going to group this, okay. Beyond this they will not even ask you, right? So that is how you're going to write it, okay. So I'll write one for vanadium as well. Let's say write it for manganese. Manganese is 25, so it will be 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2, then you have 3d5. Okay. Now again, how you are going to group this? First you will have 1s2, then you will have 2s2, 2p6, then there will be 3s and 3p. Okay. After that there will be 3d. Okay, firstly of same shell you have to write. Okay, that's how they are going to rearrange. So in electronic configuration we have studied that firstly how we fill the electrons is this way, from Aufbau principle. Then 3d and 4d will rearrange themselves, right? Rearrangement happens there. Okay, then 3s5, then you have 4s2. If you had 4p here also, they will write 4p here, right? That's how you're going to do the grouping. Firstly, tell me if you are able to understand how to do the grouping. Okay? If you're able to understand how to do the grouping, then I'll go to the next thing here, right? But for that, you need to tell me if you're able to understand the grouping, right? If you're able to understand the grouping, right? Okay. Now, from the grouping, right, what is our main task? This is the Slatter's rule, right? So in this value is constant, 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 constant. But what is not constant is this n minus 1, n minus 2. So our main task, why we did the grouping, to understand what is this n, what is n minus 1, what is n minus 2. Okay, so let's understand that firstly. So I'll firstly here teach you what is n minus 1, what is n minus 2. N is that particular electron where you are doing the, that N is that shell where you are doing, which you are experimenting with. You are saying which you are watching, or you can say which you are experimenting with. Okay, which you are doing experimenting, which we are doing experimenting. Okay, so let's say you have anything you can write. You can write for oxygen. For oxygen, it is 1s2, 2s2, 2p6, and then you have oxygen is what? No, oxygen is the 8, right? So 2p4. Okay, this is oxygen. Now, if they ask me that you have to see the screening on 2p, if they ask me, you have to see the screening on 2p. So I'll write it 3 ways, right? Screening on 2p. This is screening on 2s, right? Then there is screening on 1s. Okay, so these are the 3 things which they can ask you. Okay, they can say what is the screening effect on 2p electron, what is the screening effect on 2s electron, what is the screening effect on 1s electron, right? For that, you have to understand this thing, that if I am talking about screening effect on 2p, then this 2 will become n is equals to 2. So n minus 1 will become 1. And n minus 2 is 0, so we will not write n minus 2 here, right? Because n minus 2 does not exist. Screening on 2s means we are looking here. So again, n will become 2, n minus 1 become 1. Okay? If they ask you screening on 1s, then n will become 1. And n minus 1 is 0, so we will not write it. Okay? Now, I'm going to little bit complicate it more, right? So let's see, you have magnesium, okay? So we need to write something which is, having more shells. Let's say magnesium, or let's say sodium. Okay, I'm writing sodium. Atomic number 11, right? So it is 1s2, 2s2, 2p6, 3s1. Okay, so now let's see what you're going to write with n minus 1, n minus 2. Okay, rule you will understand, but for that first you should know that what is this n minus 1, n minus 2, what is this n, right? That firstly we are focusing on. Okay, hello, Prema, Rahul, RK, RD, what are names you have, right? Subhashri, Sai, yes. So screening on, they can ask you 3s, they can ask you screening on 2s or 2p as well. They can ask you screening on 1s as well. Okay. So if they ask you screening, firstly what I told you to write it in groups. So when you write it in groups, the groups will be like this. Okay. The groups will be like this. And the one which is belonging to same group, this is one group, this is second group, this is third group. the electron belonging to same group are always going to have same value of n and n minus 1. You have seen it here. I did it differently also. 2p same n and n minus 1, 2s same n and n minus 1. Okay, so that's why we are doing the grouping, right? Now, if you see for 3s, for this group, n will be equals to 3, n minus 1 will be 2. Okay. If they say find the screening or 2s or 2p electrons, so n will be equals to 2, n minus 1 will be equals to 1. If they say on 1s, then it will be n will be equals to 1 and there is no n minus 1. Okay, understood how to calculate n minus 1? Students, are you able to understand how to calculate n and n minus 1? Right? Are you clear on that thought? Right? Because one time I am explaining, now you can ask me 10 times also, I'll explain. But after now, then I'll start calculating the value of sigma. Then say, now how to calculate n and n minus 1? Then I will not tell you. Right now, you can ask me as many times as you can. Right? Okay. Guys, please answer. No, what is the deal? What is that big deal of like you don't even answer? Hmm? Oh. Achha, I did this. I thought I was. Oh. Okay. Okay. I'm waiting for your reply. I'm waiting for your reply, guys. Essay, it will not work. Right? Essay, even I will get bored. I will not take these. What do you want me to do? I'll teach you that atomic radius is this, ionization enthalpy is this, electron affinity is this, Lattice rules I won't teach you. Right? Then you will feel more happy. If there is some good concept, you are like literally you behave like big robots out there. Right? You have to react on something that at least you can do. After such a, you took 2 minutes, Rahul, to say. Yes, Premlata, I can see. Ramavat, I can see. But when I ask you, is that clear? Why don't you guys reply? Tell me firstly that thing. Is it that difficult? Is it that difficult to reply? Is it like rocket science? Do you have to code to reply yes? It's very simple to use. This is the keyboard. See, this is the keyboard. And if you have mobile, that is even easy. This is Y and this is E and this is S and this is M, this is A and this is M. You just have to do that. That's it. As simple as that. Not a big deal. Do I have to teach you that? Huh? Do I have to teach you that? If I join the session, now I'm on a very high energy. If you, I don't know, do you even care about that or not? I don't think so. You even care about that. Ma'am die, okay. Ma'am is dead, okay. We don't care. Huh. How does it matter? Some other ma'am will be out there. I know that doesn't matter to you. If I am alive or I am dead, that doesn't matter to you. I know that, right? So it really hurts me that we think about you so much and you don't even like literally you don't care about us, right? I was not well. I was on leave for 15 days, right? I was on medical leave. I have not taken any class and still my doctor advised me to take voice rest. And still, if you see in this glass over here, I have my medicine. I'm not able to speak without this medicine. This is still paining, but still I'm doing it for you. And this is, and you find so like, yes, ma'am, is so difficult to say. Even now, I mean, oh God, I can't believe this. Even now, you guys are literally, you are made up of which thing, yeah? Which thing you guys are made up of? Even now, you don't care to reply. I can't believe this. It's been a long time I have been teaching on YouTube, but I literally have never seen such students who find it so difficult to reply, yes, ma'am, when the teacher is teaching you these kind of concepts that you will not find on YouTube. For this, people pay 2 to 3 lakhs. That's when they get this kind of content and this kind of patience. I'm teaching you every single point in detail. So I'll not look into your chats only. I just disappointed me today. Leave. Now you will say on comments, ma'am, please don't say this, don't say that. What to do, yeah? One person replying, and I don't know how to react. You just made my weekend hell today. I'm taking classes on Saturday, Sunday, so that the gap that I had in between, so that I can fill up for that. Just for you guys. Nobody is asking me to do that. I'm already there in the batch, but I'm doing it for you, so that the students who are not able to afford the batch, they can also get good content. Just for the sake of you, I am doing this, yeah. Just for you. Do you even understand that? Chalo. Rahul, that's so sad that you are only here to understand and listen. Nobody else is actually giving a bullshit about me. They're like, okay, you see, and whatever. This is actually a big disrespect that you are throwing on my face, and I can't do anything about it. All the best. But if you can't respect your guru, if you can't respect your teacher, you will never succeed in life. Sorry about that, but that's it. If you can't respect the person who is providing you knowledge, that too for free of cost, you can't respect that person, you need to evaluate, self evaluate yourself, what kind of person you are becoming. Because I have seen my students who join my classes even after passing out. Okay, so guys, just give me a second. Okay. Now, if you see this here, this is the grouping n, n minus 1, and n, right? Now, after the grouping, as I told you, if I am talking about the last shell, that will be n, right? Then will be n minus 1, then there will be n minus 2, right? Now, let's talk about how you're going to apply this Slatter's rule. That is this one, okay? So firstly, in this rule, let's ignore this point, okay, that I'll talk about. So let's firstly not ignore this point. Let's firstly talk about this point only, right? Let's talk about if you have electrons in only one s, okay? For that, I'll be choosing helium, right? That I have written here. So I'll be choosing helium here, right? And then again, we will write it here. So first is, I'm only going to talk about this particular point, okay? I'm only going to talk about this particular point here. Other points I will not talk about, right? So here if you see, the first point is if only one s orbital you have, right? So now I'll talk about two things here. One is hydrogen and then there is helium, right? So if you talk about hydrogen, that is 1s1, right? There is only one electron. So there is no shielding, no repulsion from any side, right? So hydrogen will have no screening or shielding effect, right? Its Z effective will be equals to Z, that is 1. Sigma here will be equals to 0. No shielding, no screening will be there, right? Okay, okay, HM. That's so nice, Anshu. You're joining the session. That's great to see you guys here, right? So now let's focus on HE. This is 1s2, right? Now, if you talk about this 1s2, right, can I group it like this? Now, in this 1s2, I want to see that what is the screening on the last electron. So, last electron will be filled in 1s, right? So, if you see the screening here, right, that will be alpha is equals to, right? Now, if only one s, the rule is that if only one s orbital, like here also you have one s, here also you have one s, if only one s orbital you have, this is in case of helium, okay? You will multiply the electron multiplied by 0.30. Electron with 0.30. Now, what do you mean by this electron here? So, if you see, this is proton and here you have first electron and here you have the second electron, right? Now, usually students, what they do in 1s, ma'am, we have 2 electrons, they will multiply it with 2 and they will get the wrong answer. Why? Because we are saying this electron is going to get shielded by this one. So, always in n, you have to subtract one electron. Always the electron that you are watching screening on, that will not screen itself. This electron is not going to screen itself. But this electron is going to screen this electron. So it will be only one screening electron is there, right? Only one screening electron is there. So I can just multiply it with 1 and you will have the answer as 0.30, where Z effective is going to be Z minus, what is Z? Z is 2, number of protons in helium is 2 minus 0.30 and that is going to be the answer for Z effective. Okay. Okay, everybody. Is that clear? Is that clear? Right? Now, next is, let's talk about helium. We have already talked about. Now, let's talk about this thing. Let's talk about not this rule. Apart from hydrogen and helium, you will apply this. Apart from hydrogen and helium, you will apply this rule. But this particular rule is only valid for S and P. If you want to find the screening of S electron or P electron, only then it is valid. Wait a minute. Now, it is only valid for S and P. I'll tell you how. If there is, you're watching the screening or D electron, then this is not valid. It is even simpler. D is even simpler, okay? So, this is only valid for S and P. Let's talk about this one by one. So, let's talk about sodium, okay? What is sodium? Sodium is what? 1s2, 2s2, 2p6, 3s1. Okay. So, what I want to do here, I'll be checking screening on different things. Okay. So, firstly, I want to see the screening on. Firstly, let's say I want to see the screening on 3s. Okay. I want to see the screening on 3s. Now, this is n, this becomes n minus 1 and this becomes n minus 2. Always remember in these cases, n will be multiplied by 0.35, n minus 1 with 0.85, n minus 2 with 1 and beyond also it is 1. Right? So let's understand that how you will calculate the value of sigma. That will be the value of sigma will be sigma, right? Sigma will be number of electrons in n. You'll say 1. No, there is only one electron. There is no repulsion from any. In that row, only you are sitting. This is actually telling you the repulsion case. Only you are sitting in this one row. So there is no one other to repel you. There will be 0 multiplied by 0.35 plus this n minus 1 is 678. So 8 multiplied by 0.85, right? Plus in n minus 2 you have 2 electrons. So 2 multiplied by point, no, not point, this is only 1. And that is how you're going to have the value of sigma here. Okay. Now, here this was n minus 1. Only from n you are going to subtract 1 electron. That's why I have written 0 here. Right. Now, let's calculate what if they ask you to have electron in, let's say, 2s. Let's say they're asking you that this screening is for 2p electron. What is the screening effect if some electron is in 2p? So the value of sigma here will be, this is n, this will be n minus 1, this will be n. So in n you have how many electrons total? 6, 7, 8. In n how many electrons you have total? You have 8 electrons in n. But in that, you have 1 electron that you are experimenting with. Let's say you are 8 people. 1, 2, 3, 4, 5, 6, 7, 8. You are experimenting on this person, right? Then 1, 2, 3, 4, 5, 6, 7. 7 other electrons are causing the repulsion. Okay. So here you will write 7 multiplied by 0.35 plus this will be 2 multiplied by 0.85, and that is going to be the answer. Okay. Okay. Yes, Anshu, Sai, Rahul, Adarsh, Sanjay, HM, Aditya. Tell me, is that clear or not? Right? So, this is what we have to do here. So what is the value of Z effective? Z effective will be simple. So it is 11 protons minus sigma. That is going to be the answer. Here it was again Z effective was 11 protons minus sigma, and sigma you will calculate it from here. Right? Now for, what is the interesting part? Interesting part is that for 2s also you will get the same thing. Because if I talk about 2s here, if I talk about 2s, n will remain the same. And in that n, you will have 7 electrons only. So 2s and 2p, the one that belongs to the same group are going to have the same value of sigma. Okay? Right? No worries, no worries. Yes. Now, let's talk about sodium we have talked about. Now, this is Z effective in the last electron in 2s of neon. Okay? Neon. Okay, let's see this. Neon is 1s2, 2s2, 2p6. Right? He is asking that in 2s, you have 2 electrons. Out of this, you have to calculate. So that means this will become your n and this will become your n minus 1. Okay. So how many electrons you will have here? See, one very simple thing is, in this 2s, usually this is the biggest mistake that students do. In 2s, they usually take only 1 electron. They don't take 2p6 here because, ma'am, it is behind it. So that's why I told you do the grouping firstly. This is 1s2, this is 2s2, this is 2p6. You have to do the grouping here. So out of grouping, they are asking about 2s also. That means you have to include 2p as well here, right? You have to see the group. Group means same level they have, right? So group means 2s and 2p will be in the same shell, and same shell are going to repel each other. Okay. So if you see, this will become n, this will become n minus 1. So for sigma, n is nothing but how many electrons total? 8. 8 minus 1 is 7. 7 multiplied by 0.35 plus 2 multiplied by 0.85, and that will become your answer. Right? That will become your answer. So in 2s and 2p, you will have the same answer. Got it, everybody? Right? Right, everyone? Is that clear or not? Is that clear or not, everyone? Right? Now, this we have seen. Last electron of 2s we have seen. This also we have seen. Then there is oxygen, okay? Z effective in the last electron of oxygen. Oxygen is nothing but 1s2, 2s2, 2p6 and 2p4 actually. Okay, 2p4. So grouping will be like this. This is the grouping. First you do the grouping. After that, calculate. They are asking for last electron. Maybe 2s or 2p they are asking you. I'll take 2p as last electron. So here, this will be n. This will be n minus 1. So sigma will be nothing, that is n electron means 4, 5, 6. From n you have to subtract 1 electron because that is the electron that we are experimenting with. So 6 minus 1 is 5 multiplied by 0.35 plus 2, because in 1s you have 2 multiplied by 0.85, and you have your answer for sigma here. Okay, you're finding it easy, right? That's why I'm giving you so many examples here, right? Now we are going to change the situation. Now the situation is going to change. Let's see for D block elements, or not actually for D block, for D electrons what you do. So I told you in Slater rule that for D electron the rule is different. Okay. For D electron, let's see for D electron what you do. If you're experimenting on D electron, you want to see the screening on D electron, how you will do it. Okay. So see, simple thing is, I'll just take an example. Okay, let's see. So what you will do in D electron, you will multiply the number of electron in N with 0.35 plus beyond N minus 1, N minus 2 or beyond will be multiplied by 1. Simple. Okay. Only the electrons that are causing repulsion in N, they will be multiplied by 0.35, others will be multiplied by 1. Let's see an example. Scandium. Scandium is nothing but it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Now, write it in grouping. Wait a minute. 3p6, 3d10. This is 18. 4s2, no? So this will be 3d1. Wait a minute. My bad. Right? So now it will be in grouping, it will be written as 1s2, 2s2, 2p6, okay, 3s2, 3p6, then you write 3d, 1, and then you write 4s2. That's how you write it in grouping. Now, See, last electron we knew that that is filled in this one. After that, rearrangement is occurring. So last electron is filled in 3D. So beyond 3D, see what is happening. Firstly, electron is filling in 4s2, then there is 3D. After that, there is rearrangement again, right? So that's why after rearranging, 3D will be close to nucleus as compared to 4s. But firstly, last electron will be filled in 3D. Okay. So that's why if I see that how there is screening on 3D, so this will not matter because after rearrangement 4s is behind 3D, right? So it will not matter, right? Okay, right? IITN, I have already done that, right? You are late, so I have already done that. You can re-watch the lecture, right? Okay. So this is 3D1. This will become N. Rest of the things will become N minus 1. Rest all the groups will become N minus 1. Okay? Yes, everybody? Only the group that you are experimenting with, not even this, you should write it here. This N is group which you are experimenting with. This is only the group that you are experimenting with, right? Only the group that you are experimenting with, right? Okay, great. Right, so group is the one which you are experimenting with. This is a very important point. Sometimes students will like, we will group them together. No, this is the one that you are experimenting with. The rest, all of them will be multiplied by 1. 2, 3, 4, 5. This is 8, 10 plus 8, 18. Right, so sigma will be 1 into 18 plus 0.35 into 0. Because in 3D, you have only one electron that we are experimenting with, right? So that means there is no repulsion in 3D. Now I'll take one more example of vanadium, okay? And that is the last example that we are going to do for screening effect, right? So Z effective for the last electron of vanadium is, if you see this here, this will be vanadium is 23. So it will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. Right? Let's group them. 1s2, then you have 2s2, 2p6, then you have 3s2, 3p6, then you have 3d3, then you have 4s2. Okay? Now see one thing here. Very simple. You want to see the last electron that is filled here. Behind that it doesn't matter. Behind that doesn't matter. Right? What is in front of it is all of these electrons. That is multiplied by 6, 7, 8. That is 18 multiplied by 1. So sigma is going to be 18 multiplied by 1 plus the electrons that are causing repulsion in 3D will be multiplied by 0.35. Here you have 3 electrons, out of which 1 you are experimenting with. So you are left with 2 electrons that are causing repulsions. It will be 0.35 multiplied by 2. And that is going to be the answer here. Okay. Yes, everybody. Right, very good, very good, very good. Right, so that will become the value of sigma. And then how do you calculate the value of Z effective? Z effective will be Z minus sigma. And what is Z here? This is 23 minus sigma. That will become Z effective. Okay, that will become Z effective. Right, okay, everybody. So that was about Slatter's rule. right? That was about Slatter's rule. If you have any problem in that, do let me know in the chat box, right? Now we are going to discuss about factors affecting shielding effect. Now QE portion is going to start again. Yes, students, very good, very good, very good, very good. Rahul, Adarsh, Indu, Aitin, what's your name? What's your name? Right? So, if you see this here, factors affecting screening effect, first factor is penetration effect or power. So, we know that S orbital has a shape which will be more diffused because it is spherical shape. This is, after this, you will have, wait a minute. Huh. This should not be less diffused. Yes. Okay. Yes. This is more penetrated. This is less penetrated. Okay. I'll show you how. If you see this one, this is the spherical shape. So it will cause more penetration into the nucleus. Right? If this is a nucleus and you have a basically it's like this. This is the nucleus and you have a s orbital that looks like this. So it will cause a penetration like this. If you have 2s, it will be like this. Okay. So it will be more penetrated. But if you talk about D, so it will be like this. As you can see, this is less penetrated into the nucleus. Right? If you see F, that is even more complicated shape. So that is why S orbital has a maximum penetration, and that is the reason. And that is the reason, or should I just keep it here only so that, in notes also you can see what I was talking about, right? So because of the more penetration effect of S, then D, then F, you have screening effect of S is maximum, then you have P, then you have D, then you have F. How close the electrons are from the nucleus. If you see the inner electrons, the second thing, the effect, the shielding effect is how close is electron from the nucleus, right? If electron is here, right, then the shielding will be less. If the electron is here, then the shielding will be more, right? So, the inner electrons will produce more shielding effect while outer electrons will produce less shielding effect. That means if you talk about, I want to see this electron here. See, simple thing is that if I want to look for this particular electron and these electrons are causing the shielding, they are next to the nucleus, so they will cause more shielding. If let's say I have some electron over here, let's say I have some electron here. Now this will cause maximum shielding, then this will cause less, then even less, then even less, then even less. So more closer to the nucleus will cause more shielding because they are more attracted to the nucleus, right? Then if you talk about along the period down the group, now we're going to look forward towards the trends, right? So along the period, what will happen? As we move from left to right, in a period, the number of electrons in the inner shell remain constant. Number of electrons in the inner shell. So how does it happen? So this is basically ns1, ns2. So it happens like this. 1s1, 1s2. Then this will be 1s2, 2s2. Then this will be 2s1, 2s2. This will be 2s2, 2p1, 2s2, 2p2, and so on. So what you can see that as we move from left to right, the number of electrons in the inner shell remain the constant. In the inner shell, you have 1s2 electrons. Can you see that? Shall I just write it on the next page? Wait a minute. Let me just write it on the next page here. Right? Wait a minute. I hate it when I don't have pages to write. Okay. So let's talk about this thing, right? Let's talk about left to right, what exactly happens. right? Then we'll talk about right to left, what will happen, right? So let's talk about left to right, what is going to happen first. So if you see, this was 2s2, this was actually 2s1, this was 2s2, this should be 1s2, 1s2, right? This is group number 1, and this is how I'm writing. I'm giving you a very simple example, 1, 2, and this is group number 13. This whole will be your D block. Okay, 1, 2, 3, 1, 2, 3, 4, 5. You can write 6. That will make it more easy for you, right? So if you write it here, this will be 1s2, 2s2, 2p1, 1s2, 2s2, 2p2, 1s2, 2s2, 2p3, 1s2, 2s2, 2p4, 1s2, 2s2, 2p5, 1s2, 2s2, 2p6. So guys, now can you see one thing here, that as we are proceeding here, inner electron that are causing the shielding, that is same. Can you see? Because this is your n minus 1, this is n minus 1. These are groups only. 2s and 2p belongs to the same group. So this is the inner electrons that are causing the shielding, that are constant here, right? So inner shell remains constant, therefore shielding effect remains the same, right? Shielding effect will be same, right, in all these cases. Now if I say that across the period the shielding effect is same, right? Slightly it will differ, but very slightly, because of the 2s1 and 2s2 electron, but the inner core that is causing the shielding, that will remain the same. Repulsions will be more because of the 2s shell and 2p shell. In n is equals to 2 only, repulsions will increase. Now you can see the proton is increasing, right? Number of protons are increasing. So we can say that along the period, number of protons are increasing. If this is Z effective, this is Z minus this is constant, but this is increasing, that means this will also increase. If I say sigma is constant and this is increasing, obviously one electron you are adding, so this is increasing, so that means Z effective will also increase. So can I say Z effective here increases? Can we write Z effective here increases? Right, everybody? Okay. If you're thinking about this particular electron, this electron I told you, this belongs to the same group, right? This is causing the repulsion. Okay. So from that, very slight change will be there, which we can take it as constant, right? Now, as we move from top to bottom in a group, number of electronic shells increases. So how? Let us see. The simple thing is, if here it is 2s1, so here it will be 3s1. Here it will be 4s1. Here it will be 5s1. Then 6s1. Then 7s1. Right? So this is how it is going to look like. Right? Here it was 1s1. Right? So as you can see, before this there will be 6s also, 5s also. Right? So that means number of shells are increasing. Here the number of shells are not increasing. Right? Here the number of shells are increasing. Right? And that is the reason, right? As a result, shielding effect will increase. Because your n minus 1, n minus 2 and beyond, the electrons is going to increase in n minus 1, n minus 2, n minus 2 and beyond. Electrons are going to increase. And that is why Z effective almost remains constant, or we also say that it decreases, right? Okay, because if you see, Z effective is Z minus this. As this is increasing, this is also increasing. So this almost is constant, right? But we usually say that this decreases down the group or slight decrease. slightly decrease. Okay? Yes, everybody. Now, let's talk about next thing here, that is radius. Okay? So, based on this, I'll talk about one property, that is radius. So, let's talk about this property of radius here. So, if we talk about radius, right, atomic radius, that is nothing but covalent radius, metallic radius, and van der Waals radius, right? So, just give me a second. Let's talk about radius here, okay? So, if I talk about atomic radius, simple thing is, if I talk about atomic radius, right? In that case, I have an electron, I have an atom, right? And this is the nucleus, and this is the nucleus that I have here. This is the nucleus that I have here, right? Now, I want to see the outermost electron and the distance between this nucleus, that is called as the radius. But the problem is that atom is very small, right? So how do you calculate the radius? You can't take out one atom and calculate. Atom is generally, it doesn't look like this. If you see this here, atom in reality, where I have, wait a minute, right? If you see, if atom would have been of this size, then I would have easily calculated the radius, right? Because atom is very small, right? If I say how small is atom, in this one particular dot, you have million and trillions of atoms. Atom is that small. So how do you calculate the radius? Let's see that, right? So to calculate the radius, we have to understand three types of radius, okay? So first thing is covalent, metallic, and van der Waals radius. If you talk about covalent radius, right? If you talk about covalent radius, so you need to understand the covalent bond here. Covalent bond is formed by sharing of the electron, right? That is why it will look something like this. That is why it will look something like this. This sphere will go like this. This is the one atom, this is the another atom. Okay? It looks something like this. Now, if you see this here, if you see this here, if it is looking like this, then this is the center point, this is the center point. Okay? Now, from this center point and this center point, what you have is, you will calculate the distance here, right? So this distance that you are going to calculate from here is d, and then you see what will be the radius, that will be nothing but d by 2. Similarly, in metallic radius, what you will have? In metallic radius, see what happens in metals. In metals, what happens is, this is the structure and the atoms are next to each other. They are not sharing the electrons, they are not transfer of the electrons, they are just next to each other here, right? The boundary is colliding with each other. So that's why what you will calculate here is, from this center to this center, you will calculate the diameter here, right? D, and simple as the radius will be equals to this d by 2 approximately, right? Then you have van der Waals radius. In van der Waals radius, we talk about those two atoms which are not exactly linked to each other as such. They are not sharing any electrons, they are not sharing any boundary like metallic bonds. Here you have helium and here you have helium. They have just van der Waals interactions between them, right? There are no solid interactions, right? So that is why what you will see here, this is the center and this is the center. So what you will see, you will try to find out the distance between these two things, and that will become d. and then radius will be equals to d by 2. Radius will be equals to d by 2. No, they will not collide. That's not how metallic structures. These are the kernels and the electrons will flow here and there. That's how there is metallic structure is like that. Okay. Now, you see this is also d by 2, this is also d by 2, this is also d by 2. But can you see here that if the actual radius is x, then this will become slightly less than x. Because here this particular position that you have here, we are not taking it as separate positions. Okay, we are taking it as same position. So that's why the radius that you will calculate here will be slightly less than the actual radius. This might be equal to actual radius, and this will be slightly greater than the actual radius, right? It will be slightly greater than the collide. Why they will collide? They are sharing the electrons, no? So how covalent bond is formed? By sharing of electrons. So that's why they are making this kind of bond. So they are not colliding, they are sharing the electrons. See, in reality, this is not how atoms share. We will see that in chemical bonding, right? Actually, atom is not even a sphere, right? It's not totally, we can't say it is a sphere, right? So different structures that you have, right? So, but by assumption, we take it as a sphere only. But if you see, talk about covalent bonding, they're not colliding, they're sharing the electron, and that's how we represent the sharing of the electron. Because we'll see that in chemical bonding that, okay, I'll say that orbitals will overlap. Now, if I say this, you will get confused. So that's why I was not saying that. So basically, something will happen here and chemical bond will be formed that we represent like this. Okay? Yes. Radius, yes, we are talking about here same atoms only. We are not talking about different atoms, right? Okay, we are talking about same atoms only. You can calculate for different atoms as well. Then also you will get approximate value only, right? Okay, but you know, from this questions are not even asked, so I am not given that much importance to this one. This is just you should know this thing, right? This is an important thing, that covalent radius, because it is definitely coming out to be less than this R naught. So you can say it will be least, then metallic, and van der Waals radius will be maximum, because this extra space you are also calculating in the radius. If radius is half of it, if radius is only this much, you are calculating this extra space here, right? If here radius, if I say radius is this much, if I say, wait a minute, if I say here, this is the atom and this is the radius, but if I talk about this full diameter and if I take half of it, right, can you see it is coming out to be less than the actual radius, right? So that's why we have written it that R covalent is less, then you have metallic, then you have van der Waals radius. Okay. Yes, students. Now, next is the how radius will increase or decrease. So let's talk about that. If you talk about variation of atomic radius in the period, then what will happen? From left to right, what will happen, right? Because Z effective is increasing. That means the attraction is increasing, right? So when outermost electron is attracted by the nucleus, that is increasing, that means the size is going to decrease, right? So atomic size will decrease here because the attraction is increasing. So that's why atomic size is going to decrease along the period, right? Along the period, atomic size is going to decrease. Number of orbitals are constant here, right? That we have already discussed. Atomic radius of inert gases, this is very important. That is, you don't have to, this is from Mendeleev, that is group 0, but actually it is group number 18 in modern periodic table. Noble gases, group number 18. So what will happen? From group number 1 to group number 17, size will decrease. Then to group number 18, size will increase. Because noble gases, because of they are inert gases, they don't react, they don't form any metallic bond, they don't form any covalent bond. That's why their radius is because of van der Waals interactions, and that's why it is maximum, is highest in magnitude their respective period, because for inert gases only van der Waals radius is considered. Okay, and we have seen that van der Waals radius will be highest, and that is the reason firstly from group 1 to group 17 size will decrease, then it will increase. Okay, yes everybody. Okay, yes. Now, what we have seen, this is along the period, this is the second period, this is the second period, right? So, what we have seen from lithium till fluorine, right? Lithium, then you have beryllium, boron, carbon, nitrogen, oxygen, fluorine, size is decreasing. But fluorine, neon is going to have the maximum size. So that is the exceptional part, not even exception, that has a reason behind that, right? So neon is going to have the maximum size, and similar will be the case in third period, fourth period, that will be the same case, right? Now, if you talk about down the group, and guys, see, in periodic classification, we are only discussing about general things, okay? So if you talk about in P block and DNF block, we are properly going to see the exceptional cases. But in periodic classification, generalization will be more there, right? That's why it is so. So variation of atomic radius in a group is nothing down the group. Number of shells increases. That we have seen. 1s1, 2s1, 3s1, 4s1, 5s1, 6s1, 7s1. Number of shells are increasing, right? And that is the reason that its Z effective is almost constant, and that is the reason its size is increasing. See, 1s is like very close to nucleus, then you have 2s is here, 3s is here, 4s, 5s, 6s, 7s. So automatically size will increase because Z effective is also constant. So size will definitely increase down the group. Number of shells are increasing. Number of orbital increases, effective nuclear almost remain constant. Because of this, the effect increased the number of atomic shells overweigh the effect of increasing nuclear charge, right? So that's why what will happen here, right? Number of orbitals will overweigh and the radius will increase. So this is, if you talk about, this is the first group. This is the halogens, group number 17. This is group 1. This is group 17. Can you see down the group? Lithium, sodium, potassium, rubidium, cesium. This is fluorine, chlorine, bromine, iodine. Down the group, what is happening? Size is increasing. Size is increasing. This is the generalizations that we are studying, right? Definitely, you will see, you will see in radius also, in P block, you will see that how in radius you have exceptions, right? Okay. Now, there are some exceptional part. Most of this will discuss in D block, so that's why I'm not going to give it that much importance here. See, screening effect and Slater rule is not going to get repeated in P block or D block, but these exceptions are a part mainly of D block, right? If you're preparing for class 11, then you focus here. If you're preparing for JEE, you're automatically going to study this in D block in class 12. Right. So in the transition series, in the first series, that is 3D series, from scandium to zinc, that is 21 to 30 atomic number, how it is going to happen? There are exceptions that you see here. What is happening here? Firstly, the size is decreasing, then it is constant, then it is increasing. These are the exceptions that we will see, right? Why it is so? Simple reason is, there will be other reasons as well. So here simple reason is, increase in Z effective is more as compared to screening effect. Here Z effective is the dominating factor, right? Till chromium, the attraction of the outermost electron with the nucleus is more. Here Z effective and screening effect, as you can see here, Z effective and screening effect will become same. That's why the size is constant here. Then after that, it will suddenly increase. That is in the data, and this is a very, very important. So that's why inorganic is filled with exceptions, and these are the reasons behind that, right? Okay. Now, let's talk about group number 13. This you will discuss in P block, right? Group number 13, 14, 15, 16, 17, 18. All the things you will discuss about each exception. And this is a most repeated question of JEE. Even in 2025, and how many times it has been repeated, same question. But I really expect that they give something else now, right? So if you see in group number 13, this is group number 13. What we expect is, down the group, what should happen here? Size should increase. So it should be expected is this one. This one is expected, but this is not the reality. This one is expected, but this is not the reality. Okay? Okay? This is not the reality. Now, if you see this here, this is expected. Why this is not the reality? You know what will happen? Before this, do you know? This is what? This is the second period. This is the third period. If I see, this is second period, this is third period, this is fourth, this is fifth, this is sixth, and this is seventh. Those who now are able to visualize the periodic table, they will only able to understand this thing. We know that in fourth period, you have the addition of 3D orbitals. Before this, you will have scandium, and here you will have zinc. Before this, you will have scandium to zinc, right? And after zinc, you will have gallium, right? After zinc, you will have gallium at 31. So we know that from scandium to zinc, that is your 3D series, that is the first transition series, you are going to fill d orbitals. And we know that the screening effect, S, P, D, and then F. Screening effect of d orbitals is very poor because they have less penetration effect. And penetration effect affects screening effect that we have seen, right? So because of poor shielding, just understand one thing. What was the work? Why it was decreasing along the period? Yes. Why it was decreasing along the period? What was the work of this 3D? The work was that it should shield the electrons, right? Now, if you from aluminium to gallium, what difference has been created? Here you had no d orbitals, right? But here you had d orbitals. And d orbitals does not have a good shielding effect. Poor shielding effect they have. That is the reason that what will happen, gallium size should be more because more orbitals are being added. Because of the poor shielding effect of these 3D orbitals, the outermost electron will not be screened by the 3D orbitals, and that is the reason it will shrink. And that is because of, we also call it inert pair effect. So that is poor shielding effect of 3D orbital, that aluminium size is less than gallium. Okay. Then from sixth period, you will have the addition of lanthanoids, that is 4F. From seventh, you will have the addition of 5F, that is actinoids. Before this, you will have 4F. Before this, you will have lanthanoids and actinoids as well. Now, F has even poor shielding effect. That is why this order is going to fluctuate a lot, right? Okay. I'm going to complete this lecture after radius. Okay. I will do ionization enthalpy, electron affinity, electronegativity in the next lecture. Okay. So now if you see 4F and 5F, it is going to affect it. How do you understand that now? This 4F and this 5F is going to affect it. Now, it's a very interesting thing here. If 4F and 5F is going to affect it, then what you're going to do? The order will change here automatically, and the beautiful way of learning this order is like this. Okay, W, this is the best way of learning because learning this will be tough for you, right? So it will be okay. Now it should be like this. Okay, it should be like this. B TL, wait a minute. B wait a minute, let me just recheck it. Wait a minute. Oh, so sorry. PTLGA. No, this is for ionization enthalpy. Yes. So sorry, guys. That was for ionization enthalpy. I'm so sorry. Right, that was for ionization enthalpy. That trick was for ionization enthalpy. Okay. Now, here boron is going to be the minimum. We'll write it. Aluminium and gallium are going to replace each other. Gallium will be more than aluminium, right? After that, you will have indium, and then you will have, after that, if you say, you will have indium and thallium will be approximately same here. Approximately same, right? It will not be bigger, but it will be approximately same here. This was an easy one. Ionization enthalpy is interesting, right? Now, if you see, more exceptions will be, we know that here you have lanthanoid. These all the things we are going to do in DNF block, okay? So here you have lanthanum, and because of this, here you will have 4F series, that is lanthanoids, and because of poor shielding effect of 4F orbitals, you are going to have lanthanoid contraction. What will happen here, right? That we know that down the group, what should happen? 3D, then you have 4D, then it should be 5D. But in reality, what will happen? 4D and 5D will have approximately same size. Why? Because while going down the group, they will not have any 4F orbital. There is no poor shielding effect of 4F orbital. But they will have 4F orbital. And they will have very poor shielding effect of 4F orbital. Because of poor shielding of 4F orbital that is not capable of shielding, the outermost electron will be attracted more easily, and that is the reason instead of increasing the size of 5D because of increasing orbitals, the size because of lanthanoid contraction, the size will become similar to 5D. So 4D and 5D series will have same size, and that's why one of the example is that why zirconium is almost similar to hafnium. That's a very famous question. Okay, right? Yes, you need to remember every exception. Yes, you definitely need to remember every exception. Okay, now I'm going to talk about ionic radius because there are more exceptions to it. There is carbon family, it has carbon family, not as such, it has exceptions, but you will see in radius very few exceptions you will see, but all the other things about P block, DNF block we are going to discuss, right? In P and DNF block, right? Now let's talk about ionic radius. See, ionic radius is between a cation and an anion, right? Distance between nucleus and outermost electron in the ion. The ionic radii can be estimated by measuring the distance between cation and anion in the ionic crystal, right? So the distance that you have between these two crystals, I think you're not able to see that. Nothing here we have made. This is the nucleus, this is the cation, this is the nucleus and this is the anion, right? And the ionic radius will be the distance between cation and anion, right? Okay, right? So if you measure this distance, you can easily calculate the ionic radius divided by 2. This will be the ionic radius of cation. This will be the ionic radius of anion, right? Okay. Now, see one thing. If you have a metal, okay, one simple thing is, if you have a metal, if it is being converted to M negative, it is being converted to M positive. Which one will have more value? Now tell me, one is converted to M negative, other is converted to M positive. Which one will have more radius? Anion or cation? See here, let's say you are adding one electron and here you are taking out one electron. So when you are adding one electron, that means the size is being increased. So here the size will be M negative is going to have the maximum size, then M, and then you will have M positive. Always anion will have more size, right? Then you add one more electron, it becomes M2 negative. You take out one more electron, it becomes M2 positive. So more is the charge on the cation, the positive charge on the cation, lesser will be its size because you are taking out the electron. So nuclear attractions are increasing, right? And that is the reason the size is decreasing here. But in this case, if you see, you are adding one more electron, so that's why the size is increasing here. I'll just explain you this in a more simpler way. Okay. So guys, if you see this here, let's talk about this thing. Okay. So let's say I am saying that you have any metal or element which has, let's say six protons. Okay. Or let's say 8 protons, whatever you want to see, right? 8 protons. Now, 8 protons and there will be 8 electrons, right? M positive is going to have 8 protons, will be same always. And this is going to have 8 protons and 7 electrons. M2 positive will be 8 protons and 6 electrons. M negative will be 8 protons and 8 plus 1, 9 electrons because you are adding 1 electron here. M2 negative will be 8 protons and 8 plus 2, that is 10 electrons. Right? You have this here. Now see one thing. Okay, now let's understand one thing here. 8 protons, 8 electrons. Now here you can see 8 protons and 8 electrons, they are opposite to each other. Okay, it's like a tug of war situation, right? So when they are opposite to each other, what they are causing? They are causing like balancing each other. Now here, this party, tug of war, is the fight going on, right? This is team A, this is team B. Team proton to team electron. Now tell me who will win here? Charge is more and electrons are less. So definitely charge will win. Charge is more and electrons are less. Charge will win. When the nuclear charge is more, size will decrease. Right? Here nuclear charge is more, size will decrease. Here nuclear charge is even more, This is 8 proton, this is only 6 electron. It's like 8 people fighting with 8 people, right? Here you have 8 persons fighting with 7 persons, right? So here what will happen? 8 persons fighting with 7 persons, this is going to win. 8 persons fighting with 6 persons, this is going to win. Here you have 9 electrons, so this is going to win. Here you have 10 electrons, this is going to win. So here the nuclear charge, the attraction from this proton is going to decrease, and that's why the size will increase in an anion. Okay, right? Okay, everybody. I am about to end the lecture now, right? Okay. So that's why ionic radius is more as the negative charge will increase, because the nuclear attractions are going to decrease more you add the electrons. Proton will have no value when you add the electrons. Cationic radius is inversely proportional to positive charge. More the positive charge, more electrons you are taking. That means positive charge will cause more proton will cause more attraction, and that is why size will decrease, right? So that is why you just have to remember this particular thing, which is very, very important, right? This particular thing, which is very, very important. Now let's talk about isoelectronic species. See, isoelectronic species are those species, right, which have same number of electrons, right? For example, right, you have O2 negative, F negative, Ne, Na positive, Mg2 positive, Al3 positive. 8 plus 2, 10. 9 plus 1, 10. Neon, 10. 11 minus 1, 10. 12 minus 2, 10. 13 minus 3, 10. So all of them have same number of electrons. But protons are different. If you see, all of them has 10 electrons, but this is 8 proton, 9 proton, 10 proton, 11, 12, and 13 proton. So tell me, which will cause the maximum attraction? Maximum attraction is this is 13 proton attacking 10 electrons. Very high attraction. So size will be least here. Size will be least here. Then 12 causing 10, still attraction is there. But as compared to it, it will be less attraction. So size will be more. Here size will be more. Then 9 proton and 10. So here size will be even more. Why? Because attraction will be less. Proton, only 9 persons attacking 10 persons. Right? So size will be more. Here also size will be even more because only 8 proton. Nuclear charge is now even lesser. Right? So that's how you have the size. They will always ask you, write it in the order of size. Right? So first you need to understand that these are isoelectronic species, and there is also a simple, this what I have explained you, it's just written here, right? Number of electrons are same, but atomic number, that means number of protons are different. So you can see nuclear charge here is different. That's why the size will be like this. And you know what? What is the best way of answering this? You know, a very simple direct trick here is, anybody, how to answer this directly? Size of isoelectronic species. Size of isoelectronic species. I'm talking about isoelectronic. More is the anionic charge, more will be the size. Less is the cationic charge, more will be the size. That is your answer. Right? That is your answer. Is that clear to everybody or not? Clear, everybody? Size is directly proportional to an ionic charge, that you can apply here as well. right? Okay, let's talk about this question here, right? The correct increasing order of ionic radii. First, you have to see, are they all isoelectronic species? Calcium is 20 minus 2 is 18, right? 17 plus 1 is 18. Potassium is 19, sorry, 19 minus 1 is 18. Sulfur is 16 plus 2 is 18. So all of them are isoelectronic, that we are sure about. So more is the charge, more is the negative charge, more will be the size. So this is definitely true. But after that, it should be S2 negative, then it should be Cl, then it should be potassium, no? Potassium K positive, then it should be Ca2 positive, because more is the cationic charge, lesser is the size, more is the anionic charge, more is the size. So answer will be C is the correct answer. Okay, C is the correct answer, right, everybody? Okay, right. So that is done. Now, guys, ionization enthalpy, electron affinity, because it's already 2 hours. So I'm going to tell you ionization, enthalpy, electron affinity, electronegativity in the part 2 of this lecture, right? And there we are also going to talk about oxides and hydrides. In inorganic chemistry, you have the same. Neutral oxides, you have amphoteric oxide, acidic, basic oxides, then metallic corrector. Like there are little, very small topics that we are left with. But from oxides, hydroxides, the acidic and basic character of oxides and hydroxides, they ask the questions, right? You can see for yourself in the PYQs, they ask the questions from there, right? Okay. Yes, everybody. So that's it for today. And before going, a very important information to you. First thing is you must do your homework. And let me just see what homework I want to give you, right? This is the homework, guys. This is the homework. This is the homework question. Take a screenshot here. Take a screenshot of this question. Very simple. I think that you can do this, right? And please, start doing the homework. That is better for you only, right? Okay. So answer this one, and guys, write down in the comment section hashtag crystal clear if that is clear to all of you, and also write down your homework here, right? And guys, one more very important thing, that MV-SAT is currently going on, right? So those of you who don't know about MV-SAT, let me just tell you that what is MV-SAT. So guys, MV-SAT is a scholarship program by Vedantu where registration is completely free of cost, right? And here what you will get, right? So what you have to do is you have to give the test, and the dates are 4th, 5th, 11th and 12th of October 2025. And what will happen, ma'am? What if I get good rank here? What will happen? If you are among 2.5 lakh students here, then guys, you will get firstly 100% scholarship. You will get worth 2 crore of 2 crores of gifts like iPhone, iPads, drones, right? So that is useful. You will get the study material totally free of cost, and 100% scholarship you will get. Not even a single penny you have to pay, right? So that all is by MV-SAT scholarship program. That is a one-time opportunity. You just have to register yourself, and I would advise you, if you're thinking that, but ma'am, I have not prepared for it. Guys, you're watching these lectures, you're getting prepared only. And by October, I'll complete the syllabus. That means, and that much level is not we are going to ask you in MV-SAT. Obviously, we know that we'll ask you, see, in JEE, you have physics, chemistry, and mathematics will be asked to you, right? Total 45 questions will be there, 15 each, right? That much I think you can do. Already you are studying, right? So we are not going to ask you JEE means JEE advanced level, right? So if you watch the lectures, I think you are more than ready for the MV-SAT program, right? So I would really advise you to get yourself enrolled into that so that you can get 100% scholarship on all the courses, right? And do advise this to your juniors who are about to, or maybe in 10th class right now. There are so many students here who are in 9th class and 10th class at this point. You have this option. Just imagine you get 100% scholarship in offline centers. Just imagine that. You'll be saving so much of money. You will get prizes, iPads, iPhones you will get. Just imagine, right? You don't have to pay anything for that. So this is a one-time opportunity. I would really advise you to register yourself here, right? Especially if you're in class 11th, class 9th or class 10th. And even for lower classes also, if you're in class 7th or 8th, if your brother or sister is in class 7th or 8th, you can also apply here, because then you will be getting scholarship for class 9th and 10th. But if you're applying, let's say you're in class 10th right now, you're class 11th right now, so you'll get accordingly, you will get the batches, right? Okay. So that's it for today, guys. And next class is going to be on, see, one important thing is now I'm going to focus on class 11 classes more. Class 12th, I'll take JEE advanced questions. Reason being because we have completed physical and inorganic chemistry in class 12th. And before starting organic chemistry in class 12th, I want to complete GOC here. But to start GOC here, I'll have to do periodic classification, chemical bonding, and then GOC, right? So I'll be taking 4 classes in a week for class 11th, right? So that we can complete till GOC, right? After that, I'll start with class 12th organic chemistry, right? Simultaneously, obviously, class 11 classes will go on, right? But that's how that will open up the gate for class 12, right? Because I don't want to ruin the sequence that we have created, right? Okay, guys, chal. Okay, then everybody, bye-bye, take care, and I'll see you all in the next class. And don't forget to write it down in the comment section, your homework, and hashtag crystal clear in the comment section. Till then, bye-bye, take care, see you all in the next class. Bye-bye.